Welcome back. So this is in our first technical lecture of the course today, we're going to be talking about half spaces and the perceptron algorithm. These concepts are fundamental to machine learning, and we'll see how they apply to the very common problem of classification. So in the introduction last lecture, I mentioned an example of fall detection as a binary classification task. So in this setting, the input data was time series from an accelerometer, and in which gave us velocity and acceleration in three directions: x-axis, y-axis, and z-axis. I mentioned that our particular solution used something called a state space model, particularly a Legendre delay network, to compress a history of some rolling window into a single vector representation. And it's that vector that was used for the basis of our classifier and to get these outputs that you see in the bottom right. And so this is what the architecture of that classifier looked like. We had 9 input features, and for each one, we applied a Legendre delay network onto each one to extract that compressed vector representation. We then fed that into a hidden layer of 1,000 neurons, and it was the output of those neurons that then converged onto the output node, which returned the class. Either a fall occurred or it did not. And so as classifiers go, this is a little bit more of a complicated one in that, we're dealing with time series data and we've got this fancy state space model in there. But this architecture gives us a window into a general structure for a lot of machine learning algorithms. Specifically, everything in this box on the left here, we can call feature extraction. And then it's not doing anything directly related to the classification task, but instead processing the data in some way to make it easier to approximate functions from it. And so then once we have these features, we can learn a function from them, which amounts to figuring out the right way to combine them to get the output that we know is correct. So in machine learning, the way that these features are most often combined at that last layer just before the output is typically as a linear combination. And this method that we continue to use today can be traced back to the Perceptron algorithm, for which the first hardware implementation was achieved by Frank Rosenblatt here on the left in 1958. So this picture depicts the hardware implementation on a computer that took up the whole room. That's what was available for the technology in the late 50s. But this algorithm was actually responsible for generating a lot of excitement in AI and kicking off the field of AI, giving rise to what we know it today. So in this lecture, we're going to talk about this fundamental feature, talk about a fundamental feature shared by many of today's classifiers that was inspired by the Perceptron approach. And so by the end of the lecture, I'm hoping that you're in a position to be able to identify the components of a data set required for the supervised learning setting within which we can position classification, the classification problem. We're also going to talk about a specific hypothesis class known as the separating hyperplanes that forms the basis of the Perceptron algorithm. And I'm hoping that you'll be able to interpret this separating hyperplane hypothesis class both geometrically and mathematically. You'll also be able to go and implement the Perceptron algorithm on its own, as well as list its properties. And you'll be able to reproduce a key proof, you'll be able to reproduce a key proof and fundamental result in the field known as the Perceptron convergence theorem, which is due to Novikov. Okay, so to get us to that point, we'll be focusing our attention on 3 key questions. First, what do we need in order to learn a classifier? And so here we'll introduce the terminology that we'll use for describing data sets and introduce the mathematical notation that we'll be using. We'll then move on to defining a space of solutions in which we'd like the model to live. And this is going to provide a kind of scaffolding for learning. And so after that, we can finally turn our attention to how learning can actually happen. It's here we'll encounter the celebrated perceptron algorithm that is ultimately responsible for kicking off the field of artificial intelligence. Uh, and then we'll analyze it in depth to understand its behavior and limitations. And then close out the lecture by considering how to generalize the algorithm to the multi-class classification setting. All right. So it helps to start thinking about a simpler problem within classification, that of binary classification. And so to make sure we're all on the same page, I'd like to start off with an example. So it's the start of term, and you're probably thinking about how to prioritize and plan your work. But I'm a millennial, and so this time of year always has me thinking about heading off to Hogwarts and thinking that it does exist, and that any day now they'll be sending me a letter. They're just decades too late. And so right now I'm imagining that one of the course offerings is divination, where students learn to prophesize about future events. There's a catch though. The instructor for the course takes an extreme approach to teaching by not releasing the grading scheme or any intermediate marks and simply giving students pass or fail at the end of the semester. And so this instructor's idea is that students will be able to practice the divination skills in their real life by predicting whether or not they'll pass the class or not. And so this has meant that students have no idea how much each of their assignments is weighted for the computation of their final grade, if even such a grade is calculated. And so some students work really hard only to fail, and others do next to nothing and just breeze on through. So this has been going on for many years. Clearly, tenured professors are even harder to get rid of at these magical schools. The one semester, there's a student who is just totally unimpressed by this. She decides that they cannot possibly stomach this amount of uncertainty and is determined to figure out how to use their time to improve their chances of passing. So she decided to approach the problem by see if she could predict whether she would pass the class or not by comparing her behavior to the experience of others that have taken the course. So she starts off by reasoning that the time they spend on the course should have some relationship to whether they pass or not. And so they go out and ask those who took the class before to estimate how many hours they spent on the course, breaking it down further into time spent on assignments and time spent on the final exam, and importantly, what the outcome was, whether they passed or failed. So this table here presents a sample of the full data set collected. We can see that among this sample, students' strategies vary quite a bit, both in terms of the total time they spent on the course, as well as how they directed their time within that time. So some people prioritized the final exam, and others prioritized something else, perhaps the assignments. We can also see that 3 students passed while 3 failed. And so because the students read voraciously, she recognized that her problem was similar to that of binary classification. Binary classification is a common machine learning problem that the algorithm is tasked with solving. And so in this setting, you're given a sequence of k points or observations. And this set of observations is referred to as the training data, training set, or input data. And so then if you go and look at this data, the ith observation can in turn be described by 2 pieces of information. First, its feature vector, xi. It's often specified that xi is an element of R to the d, where d is the dimensionality of the space. And in words, the way you would read this is xi belongs to the set of real numbers in d-dimensional space. So each xi is a list of d values from the real number system. The other piece of information that we're given is the observation's class label. And so for binary classification, yi is either plus or minus 1. It belongs to the set of plus or minus 1. And so then if we were going to go and look at this data, we might expect to see a table with k rows for each of the observations in the training set and d columns to store the values for each of the data's features. The class label might then be in a final column or in another file. And so the goal of binary classification is to identify some function or mapping h such that if we were to apply it to the observation's feature vector, it would output its class label. And so ideally, this function should generalize that to data that we haven't seen before. That is, we want to be able to handle some feature vector in the same space and predict its class label. And so because it allows us to make predictions, this function h of x is called a hypothesis. So how can we learn this hypothesis? Well, an indispensable first step is to explore the data to find out if we can discern any patterns. This will tell us a lot about what kind of classifier we might need. If we spot something simple, we might not need machine learning at all. A heuristic might do the trick. A student's behavior can be characterized by just a few numbers. We can plot this easily. So this plot on the left here depicts student study strategies. The x-axis is the total time on the course, and the y-axis is the fraction of time spent on exams alone. Each point represents a student, which we've then colorized based on whether they've passed or not. And so the plot reveals a possible pattern. Students that pass put in a decent amount of total effort, but systematically deprioritized exams. On the other hand, students that failed put in more time, put in less time, or over-prioritized exams. So to put this another way, the strategies of students that passed reside in this lower left-hand corner here, whereas the strategies of students that failed lie in the upper right-hand corner. In this case, we could actually draw a line that separates those that passed from those that failed. And so to classify a new point then, we would only need to understand its position relative to that line. So how can we learn what this line is, what this line should be from data? And so for two-dimensional problems, a line can be defined by its slope, m, and intercept, x20. So learning what the line should be amounts to estimating these parameters. However, the slope-intercept form is not that intuitive or convenient to work with here. For one thing, it confuses the dependency relationships between the features of the data and the output labels. So the dependent variable in the equation is the output or the dependent variable, whereas in our data set is just another feature. And so another issue is that it only gives indirect information about whether a point is above or below the line. It's a multi-step process to figure that out. We could take the slope of the line, take the negative reciprocal, and then project each feature vector onto that perpendicular component. This isn't really a problem for computers, but anytime we have to take multiple steps in our own thinking, there's a risk that we get lost. So we'd like this process to be as direct as possible. So is there another way to write this that is more intuitive, more direct? And so it turns out that yes, another way to think about a line, is as a separating hyperplane in R2, is as the set of points that satisfy this equation, which says that the inner product between parameter vector w and feature vector x is always equal to some negatives, the negative of some scalar b. Here, both x and w lie within the set of real numbers. So this means that we do a weighted sum of the elements of the feature vector, where the individual weights are the parameters. So this says that the inner product between parameter vector w and feature vector x is always equal to some scalar b. So yeah, this means that if this equation holds for some arbitrary x given the parameters of our model w and b, then this x is on the line, or part of an affine set. So this parameterization means that we now have a direct way to test whether any new point we care about is on the line. We just need to compute the inner product and compare the result to b. If the equality holds, the point's on the line or lies within the affine set. And so if the equality does not hold, x is not on the line, and crucially, it's either going to be above or below. So the inner product operation will come up a lot in this course, and will sometimes be presented in different ways. So before we move forward, I'll just present the ways that you might see it in your textbook. So what W transpose X means is that we turn the weight vector 90 degrees and then do an element-wise multiplication between the elements of the two vectors and then sum up the results. This transpose is necessary to get the inner dimensions of the matrix to line up. That is, get a 1 by 4 to multiply it by a 4 by 1. And so this is equivalent to the sum over I of the product of Wi and Xi. And you might also see it written as see the inner product written as W comma X enclosed in these angled brackets here. So these are 4 ways to write the inner product. And so what's most convenient about this representation, though, is that the parameter vector can now be immediately interpreted as something proportional to the surface normal of this hyperplane. And the B parameter defines the extent of translation in that direction. So this reveals an asymmetry between the feature vectors in terms of the intersections on each of the axes. So for example, the horizontal intercept is now at negative B over W1, and the vertical intercept is now at negative B over W2. And so if we were to change W, we'd be changing the angle of this line. So rotating it, or kind of rotating it this way. But if we were to change B, we'd be translating it along the direction of that surface normal. And so given this information about the parameters, we now have a way to figure out the half space to which a point belongs. Specifically, we define the positive half space, H plus, as the set of feature vectors X, for which the dot product between the feature vector and the parameter vector are greater than negative B. And similarly, the negative half space as the set of feature vectors for which the dot product with the parameter vector are less than negative B. So in this particular picture, the positive half space would live above the decision boundary, and the negative half space would live below this decision boundary. And so why is this nice? Well, if we wanted to compute the distance of some point X to a line, say this one here, we can do it that what we're really interested in is the length of this line segment, which joins the point to the line, to the decision boundary, and is perpendicular to the line. And so this amounts to determining the amount of the feature vector that is in the direction of the surface normal. And this is precisely what we do when we take the inner product with the normalized parameter vector. So we then only need to check whether the magnitude of this component is greater than or less than the bias to classify the point, or add the B to it and check whether it's greater than or less than 0. So this amounts to determining the sign of the equation. In this way, we can think about W as the weights because they determine the relative weights of the features of the data in contributing to the classification, and B as a bias in making the final call for what's positive, what's in the positive or negative class. The model can also tie back to the way we think about how neurons work in the brain. So for a sample characterized by its features x1 through xd, we scale each of these by their relative weightings, W1 through WD, and then sum these all up together with a bias. We then run this through a thresholding function, indicated by this block here, to get the predicted label for the sample class. And so here the weights are kind of analogous to the number of synapses that make contact with a postsynaptic cell and cause current to flow in, where the total current is determined by summing up all such currents. And so because of this analogy to biology, these models were called perceptrons in the early engineering literature. Okay, so we've identified some basic ingredients for how to approach this classification problem. We've got our data and recognized our problem as one of binary classification, and then we've defined a class of hypotheses, that is half spaces of the separating hyperplane. That is half spaces and the separating hyperplane. So now it's time to get more specific. To find within that class of hypotheses, a single one that will allow us to make predictions. In essence, we need to figure out what those parameters W and B are for a particular data set. So how can we do that? So one framework in which this can be done is in a setting called statistical learning. So in order to apply the tools from this framework, we need a data set that respects the properties defined in this first bullet point here, which says that we need a data set with feature vectors and the associated labels that are independently and identically drawn from some distribution P. So this first part is as we encountered for the binary classification problem. And the second part relates to additional assurances that we need about the data. Specifically, IID, which stands for independently and identically distributed, means that the samples don't correlate. They're independent from one another, and identically distributed means that there's no preference for samples drawn from some parts of the distribution than others. For example, if you wanted to learn to classify hand-drawn digits, you would want a data set that was built by drawing samples at random from the population. That is, they're independent of one another and wouldn't depend on, say, the history of samples. And you would also want examples that were representative of that population, where no one sample is given special priority over another. For example, you've got examples of all such digits, and you're not just prioritizing zeros and fours, for example. So in math, the way you'll see this often appear in textbooks is as IID. And crucially, in this statistical learning setting, we assume that there is some distribution from which these samples are being drawn, but that it's unknown to us. And the goal then for this binary classification problem we've identified is to learn some function H, which maps from the space of real numbers of dimensionality D, of the dimensionality of our problem D, to the set containing plus or minus 1, such that the probability of classifying a new sample xy drawn from that same unknown distribution P is large. So statistical learning seems to make some intuitive sense, but it makes some assumptions that may not hold in practice. Specifically, it may not be true that the data we use to learn the function, the training data set, is exactly the same when it comes time to make those new predictions on the testing data set. We also might not have, strictly IID data. Samples might actually exhibit correlations and, might not perfectly cover the whole distribution. Despite these limitations, assumptions are crucial to making progress, and this provides a good starting point that often works in practice, despite the assumptions not being perfectly valid. An alternative to batch learning is online learning. In this setting, we have access to a data stream where we see a sequence of points provided to us one sample at a time. We make predictions about the labels and then get feedback on whether those predictions were good or not, and then adjust our prediction generating process. And the goal is actually to minimize the number of misclassified points that we make, where the idea of a mistake means that our predictions have diverged from some behavior exhibited by some kind of baseline for which we take as the ground truth. Crucially, in online learning, these statistical assumptions about the data are relaxed. So engineers in the late 1940s were interested in this online learning problem and came up with an algorithm to train these so-called perceptrons. Here I've shown the algorithm block for the perceptron algorithm. And what it says is that to use the algorithm, we provide an input data set D, consisting of both feature vectors xi and labels yi, where feature vectors live in the space of R to the D, and labels are either plus or minus 1. We also initialize the weights W and bias B to some value, and select some error threshold delta, which is greater than or equal to 0, to decide if a mistake has been made. Given this information, then, the algorithm outputs a choice in parameter space that approximates the solution to the problem. And so to accomplish this, The perceptron algorithm moves from the initialization in parameter space to its final position over a number of discrete time steps. T is 1 to k. At each time step, then, it receives a training sample characterized by its feature vector xt and ground truth label yt. It computes the predicted label y as the inner product of the feature vector and the weight vector plus the bias. And if the product of the predicted label and the ground truth label are less than the error thresholds, then we do some extra steps to adjust the parameters. Specifically, the product of the feature vector and the label are added to the weights, and the label is added to the bias. It is these adjusted parameters that are used at the next time step. And so to gain some intuition about why this works, let's first consider the conditions under which the parameter update is performed. So this first statement checks if the product of the predicted and ground truth label is less than the threshold, which we usually set to 0. And so assuming that it is 0, as both our ground truth labels are either plus or minus 1, if the predictions agree with the ground truth, they will be the same sign and their product will be plus 1. If, on the other hand, the prediction does not agree with the ground truth, then there will be a mismatch in the signs and their product will be minus 1. So therefore, if we set delta to 0, it means that we update the parameters when a mistake has been made. Taking a closer look at the parameter update specifically, a reasonable way to think about what's going on here is that the new weight vector rotates away from the feature vector if the label is negative, and towards the feature vector if the label is positive. Similarly, the bias is translated down if the label is negative and shifts it up if the label is positive. So that's pretty abstract. What does this look like? And so as a computational neuroscientist, a big part of my job is simulating systems to build some intuition about how they work. Visualizing things is key strategies I use to understand, get a feel for what's going on. So I went ahead and wrote my own implementation of the Perceptron algorithm. And in the next slide, we'll see a video of this in action. But before we go and watch that, I'd like to give you some context about what you can expect to see and draw your attention to a few key places. So on the screen, you'll see something that looks like this. The features of the dataset, x1 and x2, take on the horizontal and vertical axes respectively. The real-time decision boundary of the model is marked by the dotted black line, and the estimate of the parameters will appear across the top as real numbers. I've initialized them to 0. I've initialized them to start us off with this perfect 45-degree angle, but usually these are initialized to 0. We'll then start to see samples roll in to be processed by our binary classifier online. Positive samples will be orange, and negative samples will be blue and clustered in the top right. When points first appear, they'll be bright, but then they'll fade as they are kind of recede into our history. This decision boundary is going to change as we go. And so crucially, when an update occurs, we'll see the new boundary in black, and then the old boundary will be in gray. Okay, so yeah, just to give you a heads up, the first sample that you'll see will be orange and will appear somewhere in this bottom left quadrant. And what I want you to do is try to predict the new weights, given the sample the algorithm has just received. Okay, might be good now to just take a second to write down your predictions. You can pause the video. Okay, the algorithm seems to have settled into a solution, and we see that the line passes right between the positive class down here and the negative class in the up in the top right. So hopefully that visualization provided some intuition about what the update rule means. Um, I think, yeah, when I first put this together, a couple concerns I had was that if you were watching closely, you might have noticed that the decision boundary, when it was updating, would actually have misclassified points that it had seen before. Um, and yeah, another thing that really stood out to me was that the first thing that the algorithm tries to do when it sees that first positive sample is actually flip itself around. The weights were both positive, and then the first one immediately becomes negative. But yeah, I was a little bit concerned about the fact that the decision boundary would seem to kind of forget about samples that it saw before, and so I was kind of like, wait, why does this even work? Um, and yeah, I guess another concern is that will this ever converge? Can we be confident that this has now settled? Will it update again? Um, and so yeah, to get at these questions, we need to take a closer look at the perceptron algorithm. And so this algorithm was introduced almost 75 years ago. It's been studied carefully and its behavior is well understood. So that many of the questions that we raised in that last slide have kind of already been addressed. A significant fundamental result along this line of inquiry is due to Novikov and is called the perceptron convergence theorem. And so informally stated, this theorem proves that provided the data are linearly separable, the algorithm will converge. To put this another way, this means that if the data set for which we want to learn a classifier is linearly separable, that is, we could define a separating hyperplane that perfectly predicts the labels, the perceptron algorithm will converge. So the perceptron algorithm can be trusted to solve this type of classification problem. So this idea of linear separability is central to determining whether the perceptron algorithm will converge or not. The idea behind linear separability is somewhat given in the name. So, for example, if we had a data set with all positive samples in the bottom left and negative samples in the top right, we can see that they're not mixed up with one another, and crucially, that we could draw a line that perfectly separates the two classes. That is, find the separating hyperplane that makes completely accurate predictions for the labels of the data. But yeah, let's see if we can state this a little bit more rigorously in order to analyze the algorithm. So one thing that's going to help with this analysis is something called padding. And essentially what this is that instead of taking the inner product between the feature vector and the weights and then adding the bias, we first pad the feature vector with an extra element of 1, and then roll the bias into the weight vector. And so going back to our biological interpretation before, where we had a weighted sum of the features, we had a weighted sum of the features to which we added the bias before ultimately applying that thresholding operation. This is equivalent to just adding a new feature that we fixed to 1, which is weighted by B. So those were totally equivalent statements. So coming back to this hypothetical data set, and with this idea of padded data in our minds, we could kind of eyeball where that separating hyperplane should go and how it should be drawn. Yeah, we can kind of eyeball it here and have it follow this sort of gray line, the solid gray line down in the middle. And crucially, when we do that, we make it clear that linearly separable data also have to have some amount of separation between them. That is to say, there has to be some distance between the classes. And so we'll call this the margin, gamma, as the distance from the separating hyperplane to the nearest point in the data set. And so 2 gamma is the width of this band centered on the separating hyperplane. So with our eyeballing of the data set, though, we've implicitly made use of knowledge about the distribution, knowledge about the data that the algorithm normally wouldn't see. So the perceptron algorithm is an online algorithm, right? And it gets data points one at a time. But we were able to look at everything at once. So this gives us a kind of omniscience over the problem space, elevates us to a kind of oracle status, like in the Matrix movies. So we can denote this separating hyperplane that we've imagined with the associated margin as the oracle vector. It's essentially the task of the perceptron algorithm to find that oracle or something close to it. And crucially, the oracle vector is not necessarily optimal in terms of maximizing the margin of this in terms of maximizing the margin. It's just something that works, something feasible, something that correctly classifies the whole data set. Finally, one last thing, we can also simply focus, we simply focus on the direction of the oracle vector, that is normalize it so it has length or norm of 1. And so we call it the unit oracle vector. So we're now in a position to put this all together and state linear separability a bit more rigorously. So what can we say? Well, a data set is linearly separable if there exists an oracle vector, which has a norm of 1, and a margin gamma where greater than 0, such that for all features and labels in our data set D, the product of the true label and the dot product between the oracle vector and the feature vector will be greater than 0. And this last part, we've essentially multiplying the product of the true label and the predicted label using the oracle vector. So for linearly separable data with that oracle vector, we're saying that this will always be greater than 0. In other words, the true and predicted labels will agree with each other. So if we predict positive and it's actually positive, the signs match, so it's greater than 0. And if we predict negative and it's actually negative, the signs also match, and we get that positive number again. So we can actually make this more precise by stating that this product is greater than or equal to gamma. For example, if y is positive, u dot x is greater than or equal to gamma, and if y is -1, u dot x is less than or equal to negative gamma. The projection of the feature vector onto the oracle vector is at least gamma. So if we have a data set that's linearly separable as we just defined it, the perceptron convergence theorem goes quite a bit further. Specifically, if we were able to find a ball of radius r for which all samples lay within, we could say something about when it's expected to converge. Specifically, it will have converged by update k, which is less than or equal to the squared radius of the ball divided by the margin squared. So this actually gives us a maximum number of updates or mistakes that the algorithm can make. We have an upper bound on the number of errors that this thing will make as it's learning. So this is really powerful because the theorem claims that the perceptron will converge not in the infinite limit, but after a finite number of updates. It means that we don't have to wait an infinite amount of time for the algorithm to converge, but a statement like that suggests that there might be some way to predict exactly how many mistakes that might be. It's also pretty interesting that this doesn't seem to depend on things that we might expect an algorithm to depend on, like the dimensionality of the data or the number of observations. So how is it possible we can make a statement like that? And so the underlying proof is due to Novikov, and to build intuition and trust for the algorithm, we'll be going through it here today. The proof addresses 2 questions. The first point is, are we at least getting somewhere with these updates? Can we at least rule out the possibility that an update won't undo some of the previous learning? And the second question is, will we ever stop? Okay, so on to the first point. Are we at least getting somewhere with the updates? Can we rule out that possibility that we won't undo previous learning? So here we have our scatter plot of points again. We have positive examples in the bottom left and negative examples in the top right. I've denoted the separating hyperplane defined by the oracle vector, as well as the margin gamma. And so how can we define progress mathematically? Right? And so one way to think about this is that our solution gets more and more similar to the oracle vector as we go. That is, it increases its alignment with the oracle with successive updates. So another way to think about this is that the projection of the model onto the oracle increases. So for example, suppose at some iteration I, we receive the sample denoted by this orange dot here. The model would have made an error on this because the parameter vector it had just before receiving this, w subscript I minus 1, makes an obtuse angle with the feature vector in question. In this case, because the sample we received is positive, the model absorbs this example into its representation and rotates towards the sample. And in so doing, increases its alignment with the oracle of the dataset, with the oracle for the dataset. Here we went from negative result of the projection to a positive result. And so even though the magnitude of the projection is smaller than before, we've still made some progress. Similarly, you can imagine receiving another positive sample and the projection would increase again. So we'd be getting more and more aligned. That is, the angle between our model and the oracle would continue to reduce. So you might not find the oracle, but you'll get something close that perfectly separates the positive and negative examples. So we want to find out if we're making progress towards that goal on the updates. So let's take a closer look at what happens on each update. So suppose the model parameterized by W is initialized to the 0 vector. And then let's contemplate the ith update, which occurs on sample xi, such that W sub I is equal to W sub I minus 1 plus y times x. As per the Perceptron algorithm, positive examples will get added to the parameter vector and negative examples will get subtracted from the parameter vector. So to test whether the update results in an increase in alignment between the model and the oracle, we can take the dot product of both sides of the equation with the oracle u. So in this first line, we apply the dot product, and as the dot product has the distributive property, we can expand this to get the second line here. And finally, as the dot product is commutative, this last term can be rearranged to pull the y outside of the dot product between the oracle and the parameter vector. But this last term actually came up when we were defining linear separability. Specifically, we said that for all x and y, we would get something greater than gamma. That is, the component of the projection of each sample onto the oracle vector, once we correct for the sign, is at least the margin. So we can plug this into our update equation to see that the projection of the model onto the oracle will exceed that achieved in the previous version of the model by at least gamma. So no matter how small the margin is, provided the data is linearly separable, so this oracle exists, we can be totally assured that we'll make consistent progress. And as this is true for each update, by induction, we can go even further and say that after k updates, we'll have made at least k times gamma progress. That is, the projection onto U will projection of the model onto U will be at least U dot WK. So this means that we have a lower bound on the progress we'll have made by update k. It also means that the length of the parameter vector is growing because the norm has to be at least as big as its projection onto any other direction. So at update k, the norm of the parameter vector, that is the magnitude of W, must also be greater must also be at least k times gamma. Okay, so do updates necessarily result in progress? The answer is yes. And so even though we can't specify the oracle, it's really a figment of our imagination, we can still trust that our model is getting closer to finding it. we can be sure that we're getting closer to a feasible solution at every update. So we have a lower bound on the alignment and also the magnitude by update k. But as an engineer, this scares me a bit because it seems that the length of the vector could just blow up and grow to infinity. So will this happen? Will it ever stop? And this is the basis of our next question. So given this appreciation for the effect of an update on the norm of the parameter vector, we can clarify our question about will it stop to is there an upper bound on the norm of the parameter vector? So to find out, we can again return to the update equation. Although this time we can take the norm of both sides and then square it. And so once we do that, this can be expanded the equation in the fourth line here using the vector generalization of the first outside, inside, last technique I've shown on the right here. And so this gives us the square of the solution at that previous update index plus the squared norm of the feature sample times the label, and plus this last term here. But this is where things get really interesting. So this last term here is the product of the true label and the weight vector just before the update. But because we know the algorithm is updating, we know we've made a mistake. That is that the previous weight vector would have misclassified the point. There would have been a mismatch between the predicted and the true label. Their signs would be opposite from each other and therefore negative, less than or equal to 0. We can also say something about this middle term, the product of the label and the feature vector squared. Because we know that points are lying within the ball of radius r, we know that this is at most r squared. So we can rewrite this, the fourth line as this fifth line here. And this means that we are guaranteed to make at most r squared amount of progress at every update. And by induction, we can say that after k updates, we'll have made at most k r squared progress. So this gives us an upper bound on the amount of progress or alignment we'll have made with the oracle by update k. So now we can combine the lower and upper bounds. So this is the upper bound that we just saw, as well as the lower bound that we encountered a few minutes ago. So we can square the lower bounds, and then we can combine them. And so we know that the squared norm of the model is greater than k squared gamma squared, but it's less than k r squared. This then allows us to deduce that k squared gamma squared is at most k r squared. And rearranging, we can determine that k will be at most r squared over gamma squared. So that this is the basis of the claim that the perceptron algorithm will make a finite number of errors if the data is linearly separable. Yeah, so just to wrap up, this is a really fundamental result, and it's remarkable that the convergence doesn't depend on things like the dimensionality of the data, the size of the training data set in terms of the number of observations, or even the order of traversal, so the sequence in which samples are received. Okay, so a few more properties before we close out. It's important to note that the solution found by the perceptron algorithm is not unique. In fact, there's infinitely many solutions. There's no guarantee that the solution found by the perceptron algorithm is optimal in the sense that it maximizes the margin of the data set. The perceptron algorithm also won't converge if the data are not linearly separable. In this case, it'll actually never halt. It will instead cycle. And so the algorithm is not appropriate for such problems. In terms of implementing this in practice, there's a few valid termination conditions. Specifically, you could wait for the weights to stop changing. You could specify some number of updates or training budget and terminate the training once you've exhausted that. Or you can wait for the error on the training or validation step to have reached some satisfactory amount. There are different strategies for controlling the order of arrival of samples, and if you're interested, you can look those up in your textbook. And so this, I guess, but yeah, before we close out, one more comment. This hypothesis class that we've investigated really only works for the binary classification problem. So when I opened up and we were interested in this fall detection problem of saying whether a fall had occurred or not, this is an example of a binary problem because the outcome could only take on two values. But in reality, that fall detection data set has a few more outcome variables. So the output, the Y value can take on many different variables. So for example, there's different types of falls and different types of not falls. And I think there's a couple dozen different options here. So this would be called the multi-class classification problem. And so it is possible to repurpose the perceptron algorithm to give you a multi-class classifier. So one possibility is something called one versus all. And this involves training a classifier for each class. So what that means is that you select a class and then you assign one to wherever that class appears in your outcome variable. And then for every other class, that takes on a value of -1. And so you train, say if you have K classes, then you train K classifiers, and then you output the argmax over that higher level classifier, or the argmax across those lower level classifiers. Another possibility is a 1 versus 1. And the idea here is that you train a classifier for each pair of classes. So for example, if you had 4 classes, then you'd have 6 possible pairs. So you'd need 6 classifiers. And then to get a prediction, you'd output the majority vote of that ensemble. Okay, so yeah, in this, so that wraps it up for this lecture. Just to summarize, we've identified the components of the data set required for supervised learning. So we can recognize the features of a data set, the labels. I think we've identified the online and batch learning setting. We've also talked about this class of hypotheses known as the separating hyperplane, its parameterization, as well as its geometric interpretations. I'm hoping you have a strong picture in your head about that. I've also gone over the perceptron algorithm, so hopefully you can now go and code that up yourself to play with it. And we also encountered the perceptron convergence theorem, so to build trust in the algorithm and understand why, when it could fail, but also on what types of data sets we can expect it to work. Okay, so that's all for now. Thanks for tuning in, and we'll see you back here for our next lecture on linear regression.